I'd like to say hello to everyone. I'm Elise Roberts, and I'd like to welcome you to today's webinar hosted by the section on statistics in defense and national security. Today, I'm really excited to have Dr. Chris Gotwalt from JMP speaking for us. He will be giving an overview of functional data analysis and showing some of the new capabilities in JMP Pro 17 designed to help analyze spectral data that is commonly seen in chemical, pharmaceutical, and biotech industries. Dr. Gotwalt leads the statistical software development and testing teams for JMP Statistical Discovery. His interest is developing new technologies to accelerate innovation in industry and science, and he has authored a wide variety of algorithms for fitting models in JMP, including neural networks, linear mixed models, and structural equation models, just to name a few. In addition to his role as chief scientist at JMP, he holds adjunct professorial positions at NC State, University of Nebraska, and University of New Hampshire, and was the 2020 chair of the Quality and Productivity section of the American Statistical Association. Right before I hand it over to Dr. Gotwalt, I'd like to share one quick announcement. The Defense and Aerospace Test and Analysis Workshop is being held virtually and in person at the Institute for Defense Analysis in Alexandria, Virginia. And that's going to take place in April 25th through the 27th. This is a 3-day workshop. It's a multi-organizational collaboration with defense and aerospace communities, including SDNS, and showcases a combination of applied problems, unique methodological approaches, and tutorials from leading academics. The agenda, themes, and training courses can be found on the DataWorks website. Registration will be opening around the end of the month, so feel free to check out the workshop website, or you can join the mailing list to stay up to date on information. And with that, I will hand it over to Dr. Gottwald to get us started.
Thank you very much for the introduction, Elise. I'm very happy to be here and to be presenting to you guys today. This is one of my favorite topics to present about. It's been really exciting the last couple of years, kind of watching this part of the product grow. With that, I'll go ahead and get started. All right, so today I'm going to be presenting a capability of JMP Pro called the Functional Data Explorer. A lot of the time, this is it kind of introduces a new kind of data analysis to folks. So we added this because there's really a huge amount of data out there that is really inherently functional in form. This can come as time series data. We've got sensor streams coming in from manufacturing processes, especially batch processes. All the different kinds of spectra that you see in chemometrics are really good sources of functional data that we've been working pretty hard the last couple of years to improve our capabilities in. And there's a lot of different other examples, like there's DOEs where you're taking measurements over a range of temperatures or at a range of pHs or whatnot. There's a lot of different kinds of functional data out there, and we've worked pretty hard to make it a lot more easy to analyze this kind of data. I just want to acknowledge the 3 main references that we use to learn about functional data analysis. Ramsey and Silverman here is probably the Bible of functional data analysis. This was really good for us when we were learning functional principal components analysis in particular. Our early work used a lot of spline type models to convert the discrete data into continuous functions. And for that, we leaned heavily on the Rupert, Wand, and Carroll semi-parametric regression book. And then more recently, we've added a lot that takes advantage of wavelets. And this was this little Springer monograph over here by Moretin, Miniero, and Vidakovic was very, very useful to us as we were doing that. All right, so here is a plot of some functional data. This is the home price index in the state of New Jersey from 1990 to 2001. Like most functional data, it doesn't actually arrive as a continuous function. It really arises as a set of discrete measurements at a range of different X values. In this case, they happen to be equally spaced, but they can be randomly sampled in there. There's not really any restrictions on what the longitudinal variable is in a functional data analysis. And when we're doing functional data analysis, we're not really particularly interested in a single point or single measurement. We're not even really generally interested in a single collection of points that make up a single curve. Rather, we're usually interested in understanding and modeling the variation that we see across a range of different curves. So we want to understand something about the shape, or be able to predict the shape of the curves, or see what the shape of those curves says about something that we want to predict, like batch yield. Generally speaking, functional data, they always have beginning points and end points. So, and it's a little bit easier if they happen to all be in common. So here, this data set, we have all the data points are starting at 1990 here and going up to 2022. They don't have to have exactly the same beginning and end points, but it is a little bit more convenient if you do have that. What we typically do once we have the discrete measurements is we have to take the discrete measurements, convert them into like a surrogate function to turn these into continuous functions. And we have a variety of different strategies for doing that. And then the functional data analysis really operates on the surrogate functions as opposed to the discrete measurements once we obtain those. I'm just going to give a couple of other examples that we've seen over the last couple of years of functional data. This is a set of curves that came from a designed experiment where an ink manufacturer wanted to understand the clarity of an ink component across a range of temperatures. This is an example of an infrared spectra where they wanted to come up with a quick and easy way of predicting octane in gasoline based on an inexpensively obtained NIR measurement. It turned out that this curve right here was particularly informative at predicting octane. Microbial growth curves are a very common type of functional data that arises in the biotech industry. Raman spectra are also very, very common in chemical applications. High performance liquid chromatography is a very important analytical tool in the pharmaceutical and biotech industries as well. Here we see a set of reaction kinetics curves for a drug manufacturing process where we're looking at the amount of product that's created over time. We have the amount of starting material left over as a function of time. And then there's also these impurities that come in. The product will break down over time into impurities. And then also the starting material itself will break down into some serious impurities. And what they had wanted to do was find the economic best trade-off in terms of how long should they let the process run to get as much good product as they could while trying to minimize the impurities that were coming in also over time. In particular, they wanted to minimize the starting value impurities because those were more difficult to remove downstream. This is a collection of measurements that were in tanks for a fermentation process that produced a pharmaceutical product. So they would keep track of the ethanol content, the temperature, the tank level, and the amount of sugar that was in the tank over time. And they wanted to use these sensor streams in order to predict batch yield. In particular, if there was a batch that wasn't going to yield very much, they wanted to toss that batch as soon as possible and restart so they wouldn't spend time making, going through a batch that wasn't going to yield enough of the product. So why should we learn functional data analysis? Well, first of all, I find it that it's very easy to interpret the results because the shapes and curves and spectra are easy to interpret, are the primary object. You also get more accurate results because you're making more efficient use of the data than you are by pulling out kind of manual features and modeling them separately. And in JMP Pro, we've worked really hard to make these tools, as easy as accessible as possible to a wide array of different scientists and engineers. There's one kind of key problem that we've encountered over and over again that people want to use JMP Pro's data analysis capabilities for. This question is, how can I make something, a product, a process, behave according to a particular profile? And we call this functional DOE analysis in JMP, and this is where you would have DOE factors that are changing in a designed experiment kind of sense. And you want to be able to predict what the shape of a response function looks like as, as a function of those input factors. This process has sort of 5 steps to it. There's a data acquisition step, which is where you're designing the experiment and executing it. And you also have to get that data pulled into JMP, either from manual entry or pulling the data from a database or other the test equipment. Then you load it into the functional data explorer. We have data processing steps. This is where we clean up the data, isolate regions of interest, maybe do some spectral processing and so on. Then we have the very important step where we smooth or convert the discrete measurements into continuous functions. So that's where we would use splines or Fourier series. And nowadays, I've found that wavelets are very, very effective at doing this and are kind of easier to use than the other approaches in there. Automatically, once we smooth, then JMP Pro will do like a principal components type functional principal components analysis of the curves. And then once we have that in hand, we'll have sort of function specific or profile specific score values that are very analogous to principal components scores. And we model those using standard DOE modeling capabilities in JMP. And there's a very nice profiler in the functional data explorer that ties it all up in a bow and lets you kind of see what the shape of the function is as you vary those factors. Now, the core like statistical step that I think is the most important to understand is the functional principal components aspect of the analysis. So functional principal components is very much like vector principal components in that pretty much everything about functional data analysis, about functional principal components analysis, you can just take from vector principal components analysis and remove the term vector and replace function with it, and it all kind of goes through. So you, instead of eigenvectors, you have eigenfunctions. The eigenfunctions are orthogonal in a functional sense rather than an inner product functional sense rather than a vector sense. The individual curves are expressed as linear combinations of eigenfunctions and batch dependent scores, all that kind of stuff. I'm going to illustrate this with a pretty simple example that I created a while ago. This is a collection of Gaussian curves where I've randomly shifted the center point of the curve, the width of the Gaussian curve, and the peak height. So when we load that into JMP, into the functional data explorer, we see a trellis of the individual curves. We can apply a smoother that connects the dots for us. And then automatically, it gives us this principal components analysis. Here, it's found that the majority of the variation in the curves can be explained as a linear combination of 3 eigenfunctions. We've shifted our language away from using the term eigenfunction to be more approachable by practitioners. So now we call these shape components, but they're really eigenfunctions. So we can think of them in that way. And well, what I like to do when I do these functional principal components analysis is it's good to try to see if you can come up with an interpretation of what you think that shape is doing. And so in this case, it looks like the leading eigenfunction or shape component is about shape, the peak's height. So like if you had a coefficient that was large for this, it would mean that the peak was higher. If it was smaller, it would be lower down. I've kind of learned to recognize this as a peak shift type eigenfunction. It's about this, whether or not the Gaussian curve is shifted left or right. And then this is like a peak width type of shape components. This is controlling how wide the curve is. So it'd be like the sigma in the Gaussian curve. So the individual curves that we see are equal to the underlying mean function plus a shape dependent score times that first shape component plus another score times the second shape component, and another score times the third shape component. And then the rest of the variation is kind of thrown into error by this dimension reduction that we're doing. I can have a little video that shows, if we adjust the weight on the first shape component, we can see that that's causing the Gaussian peak's height to go up and down. And if we adjust the second shape component, we can see how increasing or decreasing that weight moves our curve to the left or to the right. And with the third shape component, this one is controlling the width. So this is these videos are trying to give you a little bit of a intuition around what's going on with how this dimension reduction works in a functional data analysis sense. So a little bit more on functional principal components. So here's one of the actual curves that was in the original data. So this one, is equal to approximately the function's mean in minus 0.1. So this is the functional principal component score for this batch of, this is actually peak 1. So it's peak 1 times this shape minus 6 times the shift shape and 0.2 times the third shape. So this is the most important thing here is that this is a relatively low peak because it's got a small negative value for the first functional principal component score. Peak 8 had a really high peak, so it had a large value for that first principal component. It was a little bit shifted to the right, actually, because it has a relatively large negative second functional principal component score, and it's a relatively narrow peak because it has a large score for shape component 3. Now, when we're doing analyses with the functional data, what we've done is we've taken the curves that we've observed and we've divided up the variation into 2 different sources. And then all of the batch to batch variation is explained by the corresponding weights for those eigenfunctions. And a lot of JMP's modeling capabilities around functional data is really about pulling these weights out and then modeling them, maybe like using them as responses in a least squares model or a factor forward selection type model, or pulling these weights out and using them as inputs into a neural network or some kind of a tree-based learning method. So this is really how we isolate the maximum amount of information about the curves into sort of the smallest possible representation of the data, and then we work with these.
Hey, Chris, there's a question in the chat.
Okay.
So the question is, are the 3 shape components wavelets, and where do they come from?
Okay. So these 3 shape components look a lot like wavelets. In particular, this one right here looks a whole lot like the one of the wavelet basis functions. These are shapes that are learned from the data. So like it's in the same way that if you do a principal components analysis, you've got scores that kind of explain row to row variation, and then you've got loadings that explain the variation across the columns. These have similarly been learned, just like vector principal components loadings. This data was like very carefully constructed to have very pretty, easy to interpret shape functions that look actually like wavelets, but these were entirely learned from the data.
Thanks, Chris. And we just got another question.
Great.
Will you then use the profiler to optimize these shape components?
You can do that. We have a functional principal component profiler that you can do that with. What What we do more often is we model the shape, we model these responses using least squares models. So we use the DOE factors as predictors to predict these shape components. And then we come up with a model that shoves the, instead of having the weight here in the model, we use the linear model that predicts, say, the first principal component here, second principal component's linear model here, and the third one's here. And that way we're able to kind of tie everything up into a bow where we have a profiler that's predicting the shape of the response given the actual DOE factors as inputs. And I find this to be a lot easier to interpret than the functional principal components profiler.
Oh, Chris, the question is, what does the mean function look like for this example?
So the mean function looked like this for the Gaussian peaks data.
Yeah, functionally, I mean, how would you write it down?
Oh, how would you write it down as like as a function itself?
Yeah.
Well, so that would depend on the method that you use for the surrogate model. So like if you used B splines, then it would look like a linear combination of piecewise cubics. If you used wavelets, it's a sum of wavelet basis functions. So the actual individual function itself would probably be pretty complicated because it would have a lot of it'd be some kind of a spline model or wavelet model that has like a lot of coefficients to it.
But if you had a functional form for it, could you use that?
Yes, mathematically there is a way that you can apply if you have a functional form for a set of functions, then there you could crank through the machinery and you could derive a the shape components for that family of functions that you've got. We don't have tools to be able to do this with an arbitrary like analytic function, but what you could do is load up the data. You could sample from it, and then we would smooth and obtain these kind of for you in spline or wavelet form.
Okay, thanks.
So I'm going to give an example here. I'm going to work through. So this is a real data set that came from a JMP customer. They make pharmaceutical products that need to be milled down to a specification of 70 nanometers to 85 nanometers. This milling step was a key bottleneck in the process. And so they wanted to get into the spec region as soon as possible. And they also wanted to be sure to be kind of in the middle of the spec region for as long as possible as well. So like here, if this is a milling trace of particle size over time, they wanted to get into the spec region kind of as early as possible. And they wanted to kind of stay in the middle as long as possible so that they wouldn't kind of fall out of the bottom of the specification range if there was variation in the amount of time that the batch was taking. So I'm going to kind of just jump to the end of the analysis here. So of this mill data. So this is what we call the functional DOE profiler. And on the left, we have the panel that represents the predicted curve. So in this case, it's our predicted size as a function of time. And then we have our 4 DOE factors here. And so what we want to do is we want to get this curve, to cross into the spec region as soon as possible and then stay there for as long as possible. So we can do that by adjusting the beads factor. We can move that around, and we see that pretty much by maximizing beads, we get in there as early as possible with that factor alone, but it doesn't get us, it doesn't really help us meet our goals completely. We're going to need to work with the other factors. So the second one would be strength. Looks like we'd want to probably increase strength as well. So when we do that, we're now getting into the spec region as quickly as possible. but we're shooting out of the bottom. And so we're going to see if adjusting the flow and temperature factors will kind of help stabilize the process. And it looks like minimizing flow does a pretty good job of that. And temperature doesn't do too much, but if we set it to the minimum, it looks a little bit more like it's in the middle of the spec region. So this is the interactive way that you could do problem solving with the functional DOE profiler. Now I'm just going to go through the steps as you would analyze this in JMP. So the data acquisition step is where you set up the DOE. So you give your factors, and we would go out and collect, execute the experiment and collect the data. So we have in the data set, we have a batch ID column here. We have our XY coordinates for the functions, our time stamps, and our measurements. And then we have our DOE factors for each of the individual runs. And to analyze the data, we go to the specialized modeling menu in JMP Pro to the functional data explorer. Size is our Y, X is time. We have a batch ID variable to let us know which function we're in. And we carry over our supplementary, our DOE factors as supplementary variables. This is how you communicate that we're going to use those as inputs at the end of the analysis. So we get into the functional data explorer platform. We see an overlay of all the functions here together with individual trellises of the individual batches. One thing to observe here is that in this case, the batches aren't really the same length, and the gaps between the measurements are not all the same. So it doesn't, functional data analysis doesn't require a uniform grid. What we would typically do here is initially look at the data, and then there's a whole bunch of different pre-processing commands that you can use to kind of clean up or smooth out the data. Then it becomes time for us to come up with a surrogate model that'll interpolate these wavelets. We're finding work very, very well with very little kind of mucking around with the data. So here's what happens when we do the wavelet model. It's snapped it to a grid of size 25 behind the scenes, and then the wavelet model itself is the wavelet model predictions are overlaying on the data here, and it looks like it's basically nearly interpolating the points. So this is a model that looks pretty good. Automatically, there's the functional principal components decomposition is done for us. So in this case, we've got an underlying mean function that looks like it's a slowly like an exponential decay kind of curve. The first shaped function just looks like an up-down level set, and then the second shaped function is pretty flat until we get to about 10, and then it looks like it's a slope. You can adjust the number of functional principal components that you're working with, and by default, JMP will use the BIC information selection criteria to determine the number of components, but you can kind of adjust this around and see what the impact is on actual biopredicted plots, which is a good way to see like if we're if the model is fitting well or not. So you can increase here I've increased the number of components to 5, and it hasn't really changed the actual biopredicted plot much. So we probably don't need all of those functional principal components. And we can go down to just 2 functional principal components. There's a little bit of, there's fairly similar. And then when we go down to a single principal component, we see kind of some patterns emerging over here in the actual biopredicted plot, which is kind of undesirable. And if we go to 0 functional principal components, this is using just the mean function as a model. So all of the batch to batch variation is in there, and we see that here. In this case, I'm just going to go ahead and work with the default three functional principal components that popped out kind of automatically. So this is just a review of like what this underlying model is. So we've got our model here is that we've got a mean function, and then batch 2887 is 112 times this shape minus 8.1 times this shape minus 1 or plus 1.0 times this shape, and so on. Now, what we could do is we could extract the shape components, merge it with a DOE factors table, and then model the functional principal component scores using the factors as inputs, just like a standard DOE analysis. But thankfully, JMP makes it easy for us just to automatically have this done for us by default with a red triangle menu that leads to a functional DOE analysis. What it does is goes behind the scenes and will use either best subset selection or forward selection to choose a model for each of the functional principal components, and gives you the this profiler that I've already kind of shown a little bit to let you see how modeling with the factor, how changing the factors changes your predicted curve. As an option, you can go in and you can look at the individual models of the functional principal components, and you can change them if you'd like. If you wanted to have more factors in than the forward selection model chose, you can go ahead and add more active effects or reduce them. All of the reports and diagnostics and profilers will update automatically behind the scenes to reflect the changes that you've made to the model. So this kind of makes exploring different versions of your functional model pretty easy. And then we just get to our FDOE profiler and kind of work with solving that problem with it. I'm going to just go into JMP and do some kind of live analysis. So there's a special type of situation that has come up many times. That's where you have a curve. You're trying to do curve matching. So you may have like a curve that you've identified as the best curve, and you want to find combinations of your DOE factors that will get you there as close as possible. So I've added a target curve here to the mill data that matches kind of like what we thought was going to be the best or the most realistic best case scenario in terms of matching the curve. And so I'll go through the analysis for you interactively. So we're going to bring up the functional data explorer. Our functions here are kind of expanding down as rows. So we're going to use the stacked data format for that. Size is my response, time is my input, batch is my ID, and my supplementary variables are these 4 DOE factors, not including size. So here I am in the platform. I can, in this case, since I have a target function, I'm going to load that target function up. And then at the end of the analysis, there's going to be a button in the functional DOE profiler that will find the best matching combination of factors for us automatically without having to it's cranked through. We have our functional principal components analysis, and I'm going to go to a functional DOE analysis. I haven't prettied this profiler up the way that I did for my PowerPoint presentation, but the idea is very much the same. Now, because we loaded the target, we have this optimize target button, and I can click on that, and it'll find the combination of factors that gets us closest to the target function in like an integrated L2 sense. So we're minimizing the integral squared. We're integrating that over the range of the data here, and it's found basically the same solution that I found interactively. We can actually expand by clicking on the show target profilers. So this will let us see not only the predicted size trace, but also the pointwise difference from the target, and then also the integrated square distance from the target here below. So this is one that the thing that we're trying to minimize. We're trying to get closest kind of on average in an L2 sense. Do we have any questions?
So in the last screen you were just showing, how are the eigenfunctions along the, I think those are eigenfunctions along the top row.
This here?
Yes, is that right?
No. So
What are
now
those?
these are no longer, so I'm gonna hide these. So the eigenfunctions would have, I could actually have a, turn on the FPC. So here is a profiler where we're showing the predicted size over time as a function of the functional principal component scores. So this is looking at things in terms of those extracted features that came out of the functional principal components analysis. What I'm showing down here, on the other hand, is the result of doing least squares modeling using forward selection to predict each of these functional principal component scores using the original DOE factors themselves. So this profiler, and then we kind of link up those linear models for the principal component scores along with the mean function and those eigenfunctions to construct this predicted curve right here. So that we've kind of carried things through the whole way so that you don't necessarily have to really think about the eigenfunctions themselves. It's just going from DOE factors straight to the predicted shape of the curve.
Okay, I think I understand. So you're taking an extra step. Then the
Yes.
y-axis of those 4 plots to the right, that's the same response size?
Those are so this was a 4-factor designed experiment, right? So in the original table here, we have 4 DOE factors. And so these are the things that we adjusted before we ran the batch. And then, so these are freely, independently changing variables. And then this one curve over here, this is the actual predicted trace of size over time. So the fact that these are going down, if you understand the mechanics of the jump profiler, which takes some getting used to, here, this downward trend is how size changes at this point right here for beads percent as we go from the low to high
that was the part
setting.
That was the part I was missing. Okay,
Chris.
the time slice. Got it. Okay.
Yes.
Thanks.
Chris, this is Tom. If I could maybe restate it, if you could make your window a little bigger so we can see the FPC profiler at the same time. So the FPC scores there that you can see multiply the eigenfunctions, and those create the shape of size versus time. But those aren't knobs in the process. We can't adjust FPC1 on our milling machine. So what Chris has done is he's modeled the FPC 1, 2, and 3 scores as functions of the DOE factors. And so now we can change knobs on the machine, the percent beads, the strength, the flow, the temp. And all they're really doing is changing the FPC scores that then give us the shape function. So I think that's the connection, is that you picked up there's an extra step in here, but it's that modeling of the FPC scores with the DOE factors, so we actually have hands-on control of the shape of the curve.
Yeah.
Okay.
So,
yeah, I think I got it. Thanks.
Okay.
Makes sense.
Yeah, so in here we have like individual models using the DOE factors to predict those FPC scores. So kind of suppressed a lot of the output here, so that it's not really overwhelming. But here we can see this for FPC1, it's chosen using best subset selection. The beads and strength main effects, the temperature main effect, and that's it. It's not acknowledging any of the other parts of the model. So it's just a very simple linear model. So then that gets replaced. This linear model gets used as part of this profiler down here, along with similar models for the second and third principal component scores. So I'm gonna take a look at some spectral data here, because that's the thing that we've been kind of working on the most lately. So this is an example of a very, very simple designed experiment where we have varying amounts of starch and gluten, and these so there's these batches here would have like it's all starch and no gluten. This one would be these would be 75 and 25, and so on, all the way going down to a set of batches with all gluten and no starch. And when we run it through the NIR, it creates spectra. In this case, the responses aren't kind of descending down in the rows, but they're going across in columns. So we can set up a model for this also easily without doing any data table manipulation. So go into the functional data explorer, and I'm going to spectra ID is my batch. Starch and gluten are DOE factors that we want to predict with. These are actually mixture factors, so they have to sum to one, and the profiler will know that based on metadata that's in the columns. Oh, and I need to go to the rows as functions style of input. So I put my columns in, I have my DOE factors, and I pop my batch ID in. So these are wavelengths that have intensities measured at each of them. The functional data explorer will recognize that these are numeric column names, and it will use those as the actual X values that result. So this makes it a little bit easier to understand the model and see what's going on. So here's our overlay of the batches, and there's a lot of common shapes here, but they're shifted quite a bit. So we're going to want to do some kind of cleanup on this. So in this case, there was a smoothing step that was applied first. So I'm going to use a Svitzky Golay smoother. This is going to fit a kind of a piecewise, what's kind of like a moving window polynomial model, and it's going to choose the window width and polynomial order automatically using the AICC model selection criteria. And I knew that the people that were doing this were interested in the first derivative of these shapes. So I'm going to just go to the first derivative, Svitzky-Golay smoother. And so now that's cleaned things up quite a bit. But we're going to go one step further and apply the spectral standard normal variate spectral options. What this will do is it'll take each of the individual curves now that they've been derivative transformed, and it'll make them all have mean 0 and variance 1. And so now it's really we've removed a whole lot of variation here. So we've isolated really probably what the underlying shape is of that derivative pretty well. And so then I'm going to go ahead and do a wavelet model on this again. In this case, it looks like we've really got one principal component that's really very dominant, explaining 97.5% of the variation. And then you can adjust the number of principal components that you're working with this slider. And I'll just go down to 2 in this case. I can look at these diagnostic plots to see, if I've introduced a lot more variation into the data. It hasn't done that. Actually, I like to do this kind of interactively, see what happens. So here's just the mean model that there's lots of patterns in our actual biopredicted plots and residual biopredicted plots. That's not super great. To functional principal components here seems to be doing a really good job. So I'll stick with that. And then I can do my functional DOE analysis, and we can look at how this derivative spectra changes when we adjust starch and gluten. So this is what no starch and all gluten's signature would look like, and this is what all gluten and no starch looks like. And we have kind of anywhere in between, we have a prediction for that spectra. Does this make sense to everybody? Are there any questions?
Chris, there is one question in the chat. Could a data set generated from a DOE using a split plot design be analyzed with the Functional Data Explorer?
Yes, but it's going to blow it on the split plot aspect of it. So if your p-values will not use the correct degrees of freedom. So like it's you can get profilers and stuff like that out of this, but we haven't yet put mixed models into the analysis. That's something that we're hoping to squeeze into JMP version 18.
Thank you, Chris. No other questions at this time.
I have one other example that I'll show you guys. Is a little bit more of a complicated spectra. So this is a kind of a similar data set in that we've got it's a mixture experiment in 3 factors. So these are all 3 of these are alcohols. And then we have nuclear magnetic resonance spectra for 1,000 different wavelengths. Here, kind of expanding off to the right. So model this, just go into the Functional Data Explorer again. This is a Rose's functions situation. So I'll load these up as my responses. Got my DOE factors as supplementary variables, my NMR ID. These are a little bit more complicated spectra. There's a bunch of sharp peaks. You might want to do something like focus on a particular range. It might be from we'll say 1100 to 1.1 to 1.7. So we can use the filter X option to remove everything between 2 and 1.7. So now we're able to kind of just isolate a particular region of the functions pretty easily. If we're not happy about that, or we think we've gone too far, we've got a stack of all the data transformation steps that we've done, so I can easily back off of that. There's a lot of just kind of basic transformation options available. We have some peak alignment options, and dynamic time warping is another useful option for getting your X space to kind of line up properly. As far as the spectral capabilities, I've shown Savitsky-Golay and the standard normal variate. The multiplicative scatter correction does a kind of regression. So it finds the sort of like the regression coefficients that you would use to predict, using each of the individual spectra to predict the mean function, and then kind of removes that variation from that model, kind of renormalizes using the mean spectra as a base. And then the baseline correction is a tool that allows you to kind of remove a baseline curve. So these, in chromatography applications in particular, you're interested in these peak heights, but then there's also a kind of an underlying shape in between the curves that you'd want to remove. So you can do that here with this baseline correction tool. You can add like anchor points. You're like, okay, I'm going to use this point here here, and here it'll fit like a quadratic to the values in between these points, and then subtract that from all of the functions. It does this individually to each of the functions. And so this is kind of pulled out that baseline. There isn't much of a baseline here, so it wasn't a huge change. But if there is like an underlying like exponential shape or underlying large Gaussian peak that belies all the others, it'll nicely clean that up. And then from here we can again use the wavelets, which seem to work so much better than the other options. We've got a mean spectra, and then in this case, it's found a whole lot of different eigenfunctions. I find that the BIC, for whatever reason, seems to kind of over select or under select, so we end up with kind of too many eigenfunctions. And the good news is that in functional DOE applications, overfitting in terms of the number of eigenfunctions you're working with isn't that big of a deal, because if you're, in this case, if you really mess up your model on the 20th eigenfunction, the most damage you can do is damage 1.25% of the variation in the original space. So it's overfitting here is kind of not so much of a problem. So you can kind of just dive into the functional DOE analysis, and it gives us this profiler. And we can again see what our predicted shape is as we adjust our DOE factors. This is a mixture problem, so these have to sum to 1. So that's why when I increase pentanol, because of the sum 1 constraint between these, we have to reduce the other 2 factors somehow. But you can see how this chemical NMR signature changes in a synthetic spectra kind of way using this profiler.
Oh, Chris, we do have a question in the chat.
Mm-hmm.
How would you handle analyzing data where both the response and the covariate are functions of time?
Where both an input and an output
are a function of time.
A function of time. So what I would do there is you kind of have to off-road it at that point. So what you can do is in the summaries, you would model your input and your output. So here we have this table that has all of our functional principal component scores for each of our functions, and it also we should have our it'll have other like little statistics in there. You can save these out to a data table. So I've got in this case, I have my DOE factors as well as all my functional principal component scores here. What you can do is do this for your input function and do this for your output function, and then unite the 2 data tables and use the functional principal component scores from the X variable to predict the Y variable. And then it kind of boils down to a little bit of jump formula column manipulation to be able to kind of connect the dots and be able to see how the shape of the input function changes the shape of the output function. If you review the presentations at the Jump Discovery Conference, it's one from a couple of years ago. They gave a presentation that shows how to do this very kind of thing. If you reach out to Tom, he may be able to dig up that presentation or the materials from it for you.
Yeah, so this is Tom Donnelly. You can send me an email at tom.donnelly@jump.com. There's another example by Hadley Myers where they did glycemic response curves before and after eating a snack. So you can sort of predict what that glycemic response curve would look like. And I'm sure I can find that example for you.
So does a lot of the work here, does it, you had mentioned the Ramsey book earlier.
Mm-hmm.
I know that there was a series of MATLAB scripts that that are provided with that text.
Mhm.
Is this the same? Is this different? Is this complementary? Like,
Well,
don't-
so we very rarely use uh, any like code that came from outside of JMP or SAS.
okay.
So everything here, our wavelet transform was developed natively. There's in our if I had been doing I was focusing on wavelets here, but for a long time, P splines and B splines were the surrogate model of choice, and fitting those models boils down to fitting a very large mixed model with a lot of variance components. And that entire mixed modeling framework was developed in-house. I actually wrote that part of it myself. The forward selection and the subset selection, that's all developed in-house too. So we've read those books, we've studied them, and we've used those as a starting point for the algorithms and user interface tools that we've got. But there's different times where we kind of go further than they do in terms of trying to make this as fast as possible, because we're kind of like the computational stats folks, and we're good at making this stuff kind of go fast.
Great, thanks.
And one thing I do want to just to give credit to my team. So, I lead an R&D team of statisticians that create these platforms, the user interfaces, and the all the analytical capabilities behind the scenes. And the Functional Data Explorer is the work primarily of a very talented young guy named Ryan Parker, who he's the Functional Data Explorer developer, and he's done a lot of collaboration with Clay Barker, who developed our generalized regression platform in JMP Pro. He's done some of the analytical backend, like the wavelet transform and stuff like that, that kind of underlies the new capabilities in JMP 17. I just want to make sure to give those guys, Ryan Parker and Clay Barker, I want to acknowledge their enormous contribution to this, because it's they've really done all the real work that went into making this cool platform.
I'd like to share one quick announcement. The Defense and Aerospace Test and Analysis workshop is being held virtually and in person at the Institute for Defense Analysis in Alexandria, Virginia. And that's going to take place in April 25th through the 27th. This is a 3-day workshop. It's a multi-organizational collaboration with defense and aerospace communities, including SDNS, and showcases a combination of applied problems, unique methodological approaches, and tutorials from leading academics. The agenda, themes, and training courses can be found on the DataWorks website. Registration will be opening around the end of the month, so feel free to check out the workshop website, or you can join the mailing list to stay up to date on information.